Hey everyone! Welcome back to ZoomInData. And this is episode 19 of our KQL Concepts Deep Dive series. Today we are doing a deep dive into the Hyperloglog algorithm, the probabilistic counting theory that powers dcount and approximately _count_distinct in KQL. We are keeping everything pure concepts and interview focused. If you missed episode 18 on aggregation functions philosophy, exact versus approximate, it's a perfect lead-in. Let's get started. Here is our roadmap for today. Hyperloglog estimates distinct count with very low memory. It uses probabilistic observation of hash patterns. Error is tunable, typically 1 to 2% with about 1 to 2 kilobytes per sketch. Estimates are deterministic within the same parameters, repeatable. It powers dcount in KQL for massive scale distinct counting. Understanding HLL explains why approximate counts are fast and reliable. Let's go under the hood. First, the problem Hyperloglog solves. Exact distinct count requires storing or hashing every unique value. On high cardinality data, think millions or billions of unique user IDs, IPs, or session IDs. Traditional hash sets explode in memory. They scale linearly, n space with distinct count. Hyperloglog flips that, near constant memory, log n space. The goal is to estimate cardinality accurately with tiny fixed memory and acceptable error, perfect for telemetry and logs at planetary scale. The core idea of Hyperloglog is brilliant and surprisingly simple. Hash every item into a uniform random bit string. Look at the longest run of leading zeros in binary, called the rank. The maximum observed rank across many items gives a probabilistic clue about how many unique items there are. To reduce variance, split the hash space into many buckets, typically 2 to the power of 14 equals 16,384. Compute the maximum rank in each bucket, then harmonically average them. More buckets mean lower error but higher memory, classic trade-off. This probabilistic observation of rare events, long zero runs, lets HLL estimate billions of uniques with just kilobytes. It shows exactly how Hyperloglog estimates distinct count with almost no memory. Start with any item, hash it into a random binary string. Then find the longest run of leading zeros, that's the rank. The rarer and longer that run, the more unique items are likely out there. See the small inset probability curve. Long zero runs are exponentially rarer as cardinality grows. That's the probabilistic magic. Next, track the maximum rank per bucket. Hyperloglog splits the hash space into thousands of buckets to smooth out variance. Then take the harmonic mean of those max ranks across all buckets, and boom, you get a very accurate estimate of total unique cardinality. The whole thing lives in just a tiny sketch, a few kilobytes, yet it can count billions of distinct values. No storing every ID, no linear memory explosion, just clever observation of rare patterns. This is why dcount in KQL can handle planetary scale telemetry so effortlessly, pure probabilistic genius. Error and memory in Hyperloglog are very well behaved. Standard error is roughly 1.04 divided by the square root of the number of buckets. With the common 2 to the power of 14 buckets, 16,384, you get about 0.8 to 1% typical error. Memory is roughly 5 to 6 bytes per bucket, so around 80 to 100 kilobytes maximum, even for billions of distinct items. The error is relative, Same percentage whether you're counting 1 million or 1 billion uniques. In KQL you can tune this with precision settings, low, medium, high, trading a bit more memory for tighter error bounds. Beautifully predictable. How does HLL show up in KQL? dcount builds a Hyperloglog sketch per group during aggregation. Sketches are merged incrementally as data streams in. Very efficient. Final estimate comes from the merged sketch. It's deterministic. Same input data and same precision setting always give the same estimate. Memory per group is fixed, roughly kilobytes, so it scales with the number of groups, cardinality of by clause, not with the number of distinct values. That's why dcount is ideal for per group distinct counts on massive data. Think unique uses per hour, per region, per app. Massive scale with tiny memory footprint. Take a look at this streaming flow. It shows exactly how dcount works under the hood in KQL with Hyperloglog. Data comes in as streaming rows on the left. Think live logs or telemetry pouring in continuously. For each group, say per hour, per region, KQL builds and merges a tiny HLL sketch in real time. See the low memory icon? Each sketch is just kilobytes, no matter how many unique values stream through. As new rows arrive for the same group, the sketch updates and merges incrementally, super efficient. At the end, the merged sketch produces the final dcount estimate. Lightning fast, thanks to the probabilistic math, and accurate within about 1% error, as shown by the badge. This is the magic. Massive scale distinct counting on streaming data with almost no memory overhead and blazing speed. No storing every ID, no crashing on cardinality explosion, just smart sketches doing probabilistic heavy lifting. Perfect for real-time monitoring dashboards. Why does this topic matter in interviews? Interviewers love probabilistic data structures questions. Common questions include, how does dcount work? And, why is dcount faster than count, distinct? Understanding Hyperloglog shows advanced scale knowledge. This topic is key for telemetry, monitoring, and big data analytics roles. Explaining error, memory trade-offs demonstrates deep thinking. If you can walk through how HLL estimates billions of uniques with kilobytes and 1% error, you stand out. To wrap up, Hyperloglog estimates distinct count probabilistically. It uses leading zero runs in hashes plus bucket averaging. Delivers approximately 1 to 2% error with fixed approximately 100 kilobytes memory maximum. Estimates are deterministic within the same parameters and scale logarithmically. It powers dcount for massive, high cardinality counting in KQL. This little algorithm is one of the quiet heroes that lets KQL handle planetary scale telemetry without exploding memory or taking forever. That's episode 19 done. Thanks for spending time with me on ZoomInData. Next in episode 20, percentile and ranking functions, we will explore approximate versus exact trade-offs in percentile, top N, and ranking operations. Homework to lock this in. Explain to someone or out loud. How does Hyperloglog estimate distinct count? Think of a monitoring query where dcount is better than count. Answer this one. Why can dcount handle billions of uniques with low memory? If this helped, like the video, share it with anyone prepping for Azure interviews, subscribe for episode 20, and drop a comment with your biggest takeaway today. Thank you so much for watching ZoomInData. See you next time. Keep zooming in on those concepts. Bye for now.